Statistics. Welcome to chapter 2.2. We're going to get into the heart and soul of statistics, talking about density curves. As we go through the course, we'll learn about a number of different density curves. The first one we're going to learn about, the most important one, is the normal distribution. It forms a nice bell-shaped density curve. So let's get into that. There's a lot. As I said, it's a lot. We're doing a lot. So if you want to take notes, this is not, I mean, we're gonna do this over and over again. I don't know if you need to expressly have the steps written down for this. We've been doing this, right? We're gonna calculate all these statistics to describe distributions. Already kind of been getting into that. So, and we'll go through it as a process as we do it. But here we go. So let's talk about a density curve, okay? There are rules for a density curve, right? They're always on or above the horizontal axis. Most important one, the area of a density curve is exactly 1, right? The area underneath the density curve is exactly 1. And these areas of density curves, we'll find out as we go on, can be represented as probabilities, right? And that's why they're numbers between 0 and 1, always these areas under a density curve, right? Because that's the way that probabilities work, right? Probabilities are always numbers between 0 and 1, right? 0 being that it's not happening, right? I'm 6 feet tall, 0. Right? I am teaching math right now, 1, right? That's it, right? Am I going to have a good day? I might put that at 0.5, maybe 0.3. We'll see how it goes. Anyhow, those are examples of how we would use areas underneath density curves in order to find probabilities. And that's the direction we're really moving with this. So we can look and see that this particular distribution can be represented as a density curve. This red line would be the density curve that would approximate this distribution. And that's what we're getting into. We're getting into approximating distributions with a normal density curve. It's going to be really nice. I like it. It's fun stuff, if you like. All right. So the median is going to be our equal areas point, right? It's basically the balance point, right? Of this, with the skewed data, it will not be the balance point, right? If your data is skewed, it would be off, right? Their mean is going to be the balance point. Balance point? Yeah, something like that. Most important, if your data is symmetric, if your distribution is symmetric, your mean and your median are exactly the same. If it's perfectly symmetric, the mean and the median are the same. So for a normal distribution, mean and median will always be the same because a normal distribution is always perfectly symmetric. All right, so this is a picture of what it meant, right? That balance point. And I have talked to you about how skewed data affects the mean, right? We've talked about this a bit, right? When data is skewed, the mean gets pushed out towards the tail of the distribution, right? And that's why we've talked about median being a better measure of center for skewed data. And there's a picture of that as well. We're just gonna rock through that because it's not that. All right, so this is what our normal distribution looks like. So these are normal distribution. I'll write that there. They have the same general shape, right? They can be wider or thinner depending on what the standard deviation is, right? The standard deviation of our distribution determines the width of our curve. So this guy right here is These are normal curves. All right, so got to look at these normal curves. Huh, so much going on here. All right, so your normal distribution. It is described by a normal density curve that will look very similar to the curves that we just drew in the last slide. Yesterday, I had told you about your mean being mu, standard deviation sigma. Let's talk about that a little bit more. First of all, just in case you missed it, this thing is called mu. Yep. This thing is sigma. And that's what I'll call them. I'll call them mu and sigma. It's assumed that if I call up mu, I'm talking about a population mean. It's assumed that if I write the symbol sigma, then I'm talking about a population standard deviation. Mu is mean. Yeah, yeah. And so you also saw me represent it in this way too, if we're talking about a normal distribution. Right, so if I was to write, you know, something is normally distributed, has a mean of 160 and a standard deviation of 2, it's understood automatically. We won't write mu or sigma here. It's understood by their position that mu is 160 and sigma is 2. In other words, the mean is 160 and the standard deviation is 2. So you'll get this notation put up there. And you get a lot of information from it, right? You basically know what this distribution looks like when you're given the mean and the standard deviation. Yeah. I guess we could keep talking about that. So normal distribution, this is really nice, actually. Turns out that data in the real world just naturally tends to, especially quantitative data, tends to become normally distributed, right? You'll have an average, right? The most common, what you would expect to see, right? In the middle. And then there are always some weird extreme values, not necessarily weird, but they're extreme values, right? You've always got something that kind of varies from the pattern, right? And so if you get thousands and thousands and thousands of data points, you'll get a nice bell-shaped curve distribution with most data that you would get, like, you know, heights, incomes, things like that, are normally going to follow a normal distribution if you have a large enough sample. That's the key. With a small sample, it'll look funky. But if you get a really big sample, they'll normally come out looking approximately normal. We already talked about that stuff down in the bottom. All right, this here is a friend. This is the 68, 95, 99.7 rule. It turns out that in a normal distribution, 68% of the observations fall within one standard deviation of your mean. It also turns out that 95% fall within 2 standard deviations of your mean, and 99.7% of the data falls within 3 standard deviations of your mean. So on either side. This particular rule is also called, and this is what I'm going to call it because it's way easier to say. I call it the empirical rule, and a lot of people do as well, not just me. It's so much easier to say. So if I talk about, you know, hey, we need to use the empirical rule for this, what I'm saying is we need to remember that 68% of the data is within 1 standard deviation of the mean, that 95% of the data is within 2 standard deviations from the mean, and so on, right? So that's what I'm talking about. Questions like this are super, super popular on multiple choice. All right, so I think that the explanation for this goes much better when we put it into practice with a specific example. I think it makes a lot more sense. Right now, we're just kind of being very theoretical. We'll get some real numbers in here tomorrow or during our next class. All right. Hey, I wrote this down for you guys yesterday, right? We were talking about the standard normal distribution. This is it right here. Corresponds to our z-score. You guys were on top of it and already saw that segue coming. It's hard to miss a segue. Dude on a helmet, scooting along. Just kidding. On a helmet? In wearing? Yeah, that's better. Most people aren't on helmets. All right, so guys, remember when I gave you that table, the standard normal probabilities table? I'll also call this a Z table. I like to call it that. I don't know why I call it that, but I do. I also call it, so when I refer to it, I call it a Z table. It's that standard normal probability one that I gave you. If you need another one, I have tons more. I'll always keep them on hand over there. What we use these tables for is to find, in this case now, percentiles, right? We're finding a percentile location within a distribution at this point. Later on, as we progress in the class, we'll refer to those as probabilities. So, I mean, you could start thinking about it now. These percentiles and these probabilities are the same. They're one and the same. But for now, just to keep our notation simple and the way we think about this simple, we'll talk about them just in terms of percentile location in a distribution. So the way that you use this table is if I got a z-score of 0.08. So what someone did was they did this z equals x minus mu divided by sigma, and they got this 0.08 that you see over here, right? If you want to know the percentile for a z-score of, 0.8, not 0.08, what you would do is go to that handy-dandy z table, and you would go to your z column, and you would find, it's a 0.081, my bad. There's a little glare on the screen. And you would go to 0.081, right? So you're going to look at you're going to look first of all at your row that has the 0.08. You look at the column that has the 0.01, that corresponds to 0.81. Okay? You'll find where those two meet up. That's going to be your percentile for that particular data value. And we'll do a bunch of examples where we'll actually work through that. Find a percentile from a z-score. Lots and lots of times. All right, we're gonna just do this. You don't need to write this down. If you wanted to know kind of what's going on, that's fine. But I'm gonna give you a much more succinct way to do that through an example. Normal probability plot. We'll get into this. And there we go. Got it. We did it, guys. Hey, guys, thanks for watching. I hope you have a fantastic day. And if you're not having one, smile at somebody. They'll probably smile back. You'll both be a little happier.